we're supposed to find the length of the graph, y equal 1/2 x squared plus 3, on the interval from 0 to 1, that is, from the x value 0 to the x value 1. And just real quickly, I'm just going to sketch this in real quickly so that we get an idea of what we're doing. Okay, we know it's the graph of a parabola. Let's say here's where 1 is, here's where 2 is, here's where 3 is, oops, and maybe roughly there's where 4 is. So 4, 3, 2, 1. I don't have that scaled quite correctly, do I? And we'll make this 1 on the x-axis. Okay. So when we look at that, we know we have a parabola, and it opens upward. And when x is 0, y would be 3, so that would be this point right here. But when x is 1, y would be 1/2 plus 3, or 3.5. And so we'll say, I don't have that scaled quite correctly, so I'm going to move it up a little bit. And so we're talking about this part of the graph. We want to know that length. And clearly it's a little bit more than 1, isn't it? Okay. Well, to do this, we need to remember first how we calculate arc length, or the length of a curve. So recall that L, length, is the integral from A to B of the square root of 1 plus f prime of x, the quantity squared, dx. Now, in the case that we don't really have an f function by the name of f, we can also, of course, use the notation derivative of y with respect to x. So it's the integral from a to b of the square root of 1 plus the derivative of y with respect to x, and that derivative is squared, and we're taking the integral with respect to x. So in this case, okay, for us in this problem, the derivative of y with respect to x is simply x, isn't it? The derivative of 1/2 x squared plus 3 is just simply x. So we set up to do our calculation. The length is equal to the integral. Our first x value is 0 to an x value of 1. That's our a and b, times the square, of the square root of 1 plus our derivative squared. And our derivative is x, and so that's x squared, of course, there. Oh, well, this is nothing more, okay? This is nothing more than the kinds of things that we've been working on. We have an integral that is the integral of the square root of 1 plus x squared. And this is a form where we're going to use a tangent substitution. So we're going to replace x simply with tangent of theta. And while we're here, let's find out what dx is going to be. Dx, well, what's the derivative of tangent of theta? Secant squared theta, isn't it? So dx is secant squared theta d theta. Okay? Now, we go a little, and by the way, well, we'll just leave it at that for right now. We're going to do our substitutions now. So let's remember, though, I'm going to make a notation here. This 0 is an x value, so let's not be confused with that later on. And this 1 is an x value. So we've got the square root of 1. X has been replaced with tangent of theta, so this is 1 plus tangent squared theta. And dx is being replaced with secant squared theta d theta. Now, in this case, let's see here. This is an x value. This is an x value. 1 plus secant squared theta is the same as, 1 plus tangent squared theta is the same as secant squared theta. So under the radical, we have secant squared theta. And of course, times secant squared theta d theta out here. But of course, the integral of secant squared theta is nothing more than, the square root of secant squared theta here is just secant of theta. So we have the integral from x equals 0 to x equal 1 of secant cubed theta d theta. Now, we have a bit of a choice to make here. We can convert, well, okay, let's go another step, though, before we go any further here. The integral of secant cubed theta from your notes, and this is an important integral for us, we see very often. So from our notes, the integral of secant cubed theta is 1/2 times the secant of theta times the tangent of theta plus 1/2 times the natural log of the absolute value, natural log of the absolute value of secant of theta plus tangent of theta. Those absolute value. And of course, we're evaluating that from an x value of 0 to an x value of 1. So we have a choice. We could convert those x values into theta values and plug them in, or we can convert each of those trig functions back to x values. And it really doesn't matter which one we choose. I think to mix things up a bit here, just to do things a little differently, and this hasn't been an option before now because we didn't have a definite integral. And so we would have had to convert our theta business back into x business, and we'd use a representative right triangle. But remember on this substitution, when we first started this discussion about dealing with these substitutions, that we said in the case of a tangent substitution, we're going to assume that theta is between negative pi over 2 and positive pi over 2. And so what I'm doing is I'm looking to replace these two x values with theta values because everything's in terms of thetas. And so I could say, well, now if x is equal to 0, remember from above, x is the tangent of theta. So that would say the tangent of theta is equal to 0. And that only happens for between negative pi over 2 and positive pi over 2 if theta itself is 0. Now, on the other hand, if x is equal to 1, well, from above, that means the tangent of theta is equal to 1. And for values of theta between negative pi over 2 and positive pi over 2, that can only happen if theta is pi over 4. So we can change our limits of integration or our limits of evaluation to dealing with, at the lower end, theta is equal to 0, and at the upper end, theta is equal to pi over 4. So we'll change, now we don't have to go back to x's. Okay. And we have an absolute value here. So this is going to be theta equals 0 and a theta equal pi over 4. And we can just do those substitutions. And I'm not going to go through the tedium of doing those substitutions and calculating, but I tell you after it's all said and done, this is what I would get. I would get the square root of 2 divided by 2 plus 1/2 times the natural log of the absolute value of the square root of 2 plus 1. And then I could write that a little differently because I have two fractions with a denominator of 2. So I could write it as the square root of 2 plus the natural log. Now, square root of 2 plus 1 is positive, so I don't really need the absolute value symbols there, do I? All divided by 2, that's the exact value. If I got that doesn't tell me a whole lot, I don't know about you. If I got my calculator out to approximate that, my calculator would tell me this is about 1.1478. So the length of that curve that we've drawn is just a tiny bit more than 1 unit long, 1 1/1500ths of a unit long, isn't it? That gives you a little different twist from things that we've been doing. Now, I'm going to follow this up with a couple of more examples where we're doing integration by trigonometric substitution. But there's going to be a little twist to each of the next two examples that I give. So in this example, you see that we're to evaluate the integral of 1 over x squared plus 8x plus 25 to the power 3/2, a quadratic to the power 3 halves. Of course, 3 halves means we have a square root involved. Now, because we have all positives, you know, the only thing that we could hope for, let's make a note of this, the only thing that we could hope for is to have something of the form, and I'm not ignoring that it's in the denominator, but of the form a squared plus u squared, or vice versa. That's what we would have to hope for. You know, we've got a square root to the power 3, really, is what we have. So we're hoping to be able to get this into, if we're going to have any luck at all, we're hoping to be able to write that quadratic in the form of a squared plus u squared, where u is the variable part and a is a constant. Now, this leads me to think about if I could actually have a perfect square trinomial, then it would factor as binomial times binomial, where the binomials are the same, and that could act as my u. So what I'm thinking here is we should consider completing the square. Okay, so let's take this trinomial, x squared plus 8x, and let's kind of think about putting the plus 25 over here, because we're wanting to create a trinomial in this position that we can factor as a perfect square. And so if you recall, the way we do that is we take 1/2 of the coefficient in front of the x to the first degree term, which is x to the first power, and we get a 4. Well, then we turn around and we take that 4 and we square it, and we get a 16. So we actually need a 16 right here. Now, once I've done that, I've changed my trinomial. I've changed my quadratic. I added 16. So at the same time, I'm going to subtract a 16. Now I've got exactly the same thing. But the x squared plus 8x plus 16 can actually be factored as x plus 4 squared. And over here, the 25 minus 16 is just a 9. And so you can see that we really have this in the terms of a u squared plus an a squared. Okay, and it doesn't matter whether we have the variable, because of the plus, it doesn't matter whether the variable part's first or last. So that gives us a hint on what we want to do. We're going to come over here. I'm going to start over here on the edge because I keep running out of space. Okay, we're going to come over here and we're going to evaluate this integral. We're going to try to use trigonometric substitution. And so the first thing we're doing is we're using the fact that we can complete the square in that denominator. And so the way we're going to write this denominator is 9 plus x plus 4, the quantity squared. And that whole thing, of course, is to the 3/2 power, and we're integrating with respect to x. Well, now that leads us to the idea, okay, that the x plus 4 is really our u value, isn't it? And the 9, well, actually, the 3 is actually our a value. And so if we do this by prescription, then we replace u with a times, because we have a plus, this is a tangent substitution, a plus tangent of theta. But of course, u is x plus 4, and a is 3. So in the place of x plus 4, we're going to put a 3 tangent theta. Well, when we do that, of course, then we have a 9. We don't change that, but the x plus 4 is being squared. And so when we square x plus 4, that means we've got to square this 3 plus tangent of theta, and so that gives us 9 tangent squared theta. And of course, that's raised to the power 3/2. Now, we still have some work to do. But this step, at least, we're fairly complete. And let's just think about what's going on. We're going to factor out a 9, and so we'll have 9 times 1 plus tangent squared theta. And that 1 plus tangent squared theta we can turn into a secant squared theta. So what we really will have down here is 9 times secant squared theta to the power 3 halves. Now we're still going to have to deal with this dx, and we will deal with that in just a second, but let's go ahead and simplify further this denominator, because that really says we're taking the square root of 9 secant squared theta, and then we're turning around and cubing. Well, when we take the square root of 9, of course we get 3, but when we cube that, we'll get 27. And when we take the square root of secant squared theta, we'll get secant theta, but when we cube that, we'll get secant cubed theta. Now, let's turn our attention to this dx. To figure out what dx is, we need to know what x is. And right here, we can say, oh, since x plus 4 is equal to 3 tangent theta, then x itself is 3 tangent of theta minus 4. And that allows us then to calculate dx, because that we're going to just take the derivative of the right side with respect to theta. Well, the derivative of tangent theta is secant squared theta, so we get 3 secant squared theta, and of course the derivative of a constant is just 0. So we get 3 secant squared theta d theta as our dx. Well, now we're in a position that we can rewrite this now. We'll replace our dx. So we have 1 over 27 secant cubed theta, and dx is 3 secant squared theta d theta. And you see now we have opportunities for a simplification. We have a 3 over 27, which is 1/9. We'll factor that out. We have secant squared over secant cubed, which is 1 over secant to the first power. Let's simplify it a lot. And of course, 1 over secant theta is nothing more than cosine theta. So this is 1/9 times the integral of cosine theta d theta. Well, that's easily done. The integral of cosine theta, of course, is sine theta. And now plus our constant integration. But what are we left with? We've got to still revert back into x's. So now we use the idea of our representative right triangle. So here's theta. Now, remember, we started out with x plus 4 is equal to 3 tangent of theta. We need to solve that for tangent of theta, and when we do, we get tangent of theta is x plus 4 over 3. Well, now tangent is calculated by saying opposite over hypotenuse. So the x plus 4 will represent the opposite side from theta, and the 3, what did I say? I said that incorrectly. Remember, the tangent of theta is opposite over adjacent. I think I said over hypotenuse. My bad. And so that means the 3 is the side adjacent to the angle theta. And then we'd use the Pythagorean theorem and determine that the hypotenuse ends up being the square root of 9 plus x plus 4 squared. Now, of course, that will simplify further. We'll wait for a moment to do that. Okay, now we're ready to calculate sine theta based on that triangle. Well, sine of theta is opposite over hypotenuse. And the opposite side from theta is x plus 4, and the hypotenuse, of course, is the square root. The square root of 9 plus x plus 4 squared, plus our constant integration. And only, I would do probably a couple of last things. I would multiply the 9 with that denominator, And under that radical, that's kind of a strange way to leave our result. You know, that's really what we started with originally as x squared plus 8x plus 25. I mean, that's all we really did is we changed the form of x squared plus 8x plus 25. So if we were to multiply that out and add terms, we would get x squared plus 8x plus 25 under that radical, plus our constant of integration. So that's a little technique that we can always consider, and we've seen that throughout the semester. Completing the square is very useful occasionally. Well, this last example of this section, trigonometric substitution that I'm doing, is a little bit of a different type of tangent substitution. I say strange because we don't have polynomials that we're dealing with here. So as you can see, we're to evaluate the integral e to the 4x times the square root of 1 plus e to the 2x with respect to x. Now I'm looking at underneath that square root, I have a sum, which means I'm thinking about a tangent substitution immediately. And of course the constant is 1, and that represents 1 squared, and so we're here with the idea that a is going to have to be 1. So what is u? Well, we have to square u to get e to the 2x. And so that means u would have to be e to the x, because when we square e to the x, we multiply the x and the 2, we will multiply those two exponents, and we would get the exponent of 2x. So now we see that this is of that form, okay? So we need to replace e to the x, if you will, with tangent of theta. Now, I mean, hopefully after we practice this, we could immediately go to say, oh, I'm going to make e to the x tangent of theta. And so then I recognize when I square e to the x, I'll get tangent squared of theta, because I'm doing this for a particular reason. And of course, when I square e to the x, I get e to the 2x. So in that position of e to the 2x, I can replace it with tangent squared theta. Now by prescription, that is what we said at the very beginning of all of this, is we were going to replace u with a times tangent theta. That's how we said that this was going to be done. So in this case, u being e to the x would be replaced with 1 times tangent of theta, and that is exactly what we said up above. E to the x is going to be tangent of theta. So once we recognize that, let's see all of the business that we've got to deal with here. Okay, we're going to evaluate, so I'm going to write down the integral of e to the 4x times the square root of 1 plus e to the 2x dx. And we're going to use trigonometric substitution. So we're going to have to replace e to the 4x, and we're going to have to replace dx as well. Okay. Well, but to replace e to the 4x, we've got to take, we already decided e to the 2x. We already decided that e to the 2x is tangent squared theta. So we have a replacement for that, don't we? In the case of e to the 4x, how are we going to calculate it? Well, recognize that e to the 4x is nothing more than e to the x being raised to the 4th power. And so that means we have tangent to the 4th theta. So e to the 4x is tangent to the 4th theta. Square root of 1 plus, now e to the 2x we decided is tangent squared theta. Now there's a sticky little deal about d theta. Now d theta is not so easy, okay? I mean, we have to be clever, I guess is what I mean. I'm thinking about how I'm going to do this. Yeah. Here's the only thing that I've got that relates the x and the thetas. The simplest thing I've got that simplest thing is that e to the x is equal to tangent of theta. So my suggestion is we take the derivative of both sides with respect to x. Okay? Excuse me, with respect, with respect to x. Well, the derivative of e to the x with respect to x is very clearly just e to the x. Now, in the case of the derivative of tangent of theta with respect to x, we have to use the chain rule because we're not taking the tangent of x. So to take the derivative of tangent of theta with respect to x, what we do is the derivative of tangent is secant. So we get secant squared theta, but then we have to take the derivative of that, what the tangent is of, theta, with respect to the variable x. Aha. Well, if we look at that, then we've got several things going on here. For one, what are we trying to do? We're trying to get dx alone, aren't we? We're trying to get dx alone. So we could multiply both sides by dx now, so we'd have dx times e to the x, or let's write it this way. E to the x times dx is equal to secant squared theta d theta. But the problem is we only have a dx above. We don't have an e to the x dx. And then it dawns on us, maybe, hopefully, that e to the x is tangent of theta. So this is really tangent of theta dx is equal to secant squared theta d theta. And so now we can solve for dx by dividing both sides by tangent of theta. So dx is secant squared theta divided by tangent of theta d theta. Now we have a replacement for dx. And so we'll put that right up here. It's secant squared theta divided by tangent of theta d theta. You have to admit that was not on my part particularly, but that was a little clever bit of work, and we had to take several steps to do it. But we don't learn anything unless we see examples of the unusual. Okay, well, let's go up above now, and let me kind of bring this over because I'm running out of room again. So let me bring this over to where this is where my equal sign is. Okay, I'm just going down what we've got there. And let's see what we can simplify. Well, for one thing, under this square root, 1 plus tangent squared theta is nothing more than secant squared theta, isn't it? And so we'll have this tangent to the fourth theta. And when we take the square root of secant squared theta, we get secant of theta. And then we have times the fraction secant squared theta over tangent of theta d theta. Now, I think we can do a significant amount of simplification here. Okay, I believe we can. I say a significant amount. We'll have a tangent to the fourth over tangent, which is tangent cubed, isn't it? So we have the integral of tangent cubed theta times secant cubed theta d theta. Now, what can we do next? Well, what we have here is an integral of powers of tangent and secant, which we've dealt with in the previous section, haven't we? And I think what I would like to do, I'm going to, usually we said u is equal to, but I've already used u over here on the upper left. I guess let's just kind of put aside that we've used u before and just come back to the idea that I'm going to do a u substitution, but it's in a special way, of course. So my choices are u can be tangent of theta or u can be secant of theta. And I'm thinking I'm going to let u be secant of theta. So here's what's going to happen. If u is equal to the secant of theta, then du is the derivative of secant of theta, which is secant of theta tangent of theta d theta. So if I'm going to be successful in integrating this by letting u be secant of theta, what I'm going to have to do is strip away a secant theta tangent theta. So I'm going to write this as tangent squared theta times secant squared theta, and then I'm going to write times secant of theta times tangent of theta d theta. So this is going to end up being my u. My du. And this is going to end up being u squared. Now the problem is the tangent squared business. Okay? Well, tangent squared can be written in a way in terms of secants. And since u is secant, then we can convert it all into u. So tangent squared, of course, is secant squared theta minus 1 times the secant squared theta that we already have here times the secant of theta tangent of theta d theta. So as we do our conversion, then this ends up being the integral of secant is u, so this is u squared minus 1 times u squared, and of course all of this is the du again, so times du, or with respect to u. Now that looks like that's actually pretty simple, because if we multiply that u squared out, we'll have the integral of u to the fourth minus u squared with respect to u. And of course that's easy enough. That's 1/5 u to the fifth. But of course u is secant of theta, so that's 1/5 times secant to the fifth theta, minus the integral of u squared is 1/3 u to the third. But of course u is secant, so it's 1/3 secant cubed theta, plus of course our constant of integration. So now to finish this off, we've got to go back and replace our theta business with x business. And so we need that right triangle. Okay. Well, here's the angle theta. Now the information we have, remember the information is way back up here, and it is that the tangent of theta is equal to e to the x. That's what we started with. And when we want to write that as a fraction, e to the x over 1, because tangent of theta is opposite, so there's the opposite side, over adjacent, there's the adjacent side. And then if we use the Pythagorean theorem to determine the value of the hypotenuse, we would end up with the square root of 1 plus e to the 2x. Now, we need to replace secant. So secant of theta, being the inverse, the reciprocal of cosine, would be hypotenuse divided by adjacent. And in this case, the hypotenuse is the square root of 1 plus e to the 2x. And of course, the adjacent side is just 1. Okay? So here's what we have. We're going to replace secant with the square root of 1 plus e to the 2x. And of course, that's raised to the fifth power here. Minus 1/3, we're replacing secant with the square root of 1 plus e to the 2x. And of course, that's raised to the third power, plus our constant of integration. And probably what I would do if I was finishing this off and making it look the way would be most common is I would consider that Square root of 1 plus e to the 2x is 1 plus e to the 2x to the power 1/2. And so that would give me 1 plus e to the 2x with a power of 1/2 times a power of 5. So that would be a power of 5/2. And in a very similar fashion over here, we would have minus 1/3 times 1 plus e to the 2x to the power of 3/2 plus our constant of integration. Well, that again, that was a little bit strange, but if we don't see unusual situations, then we may not be prepared for the things that we see in homework or on the test or later in life when we're dealing with some mathematics. Well, that's the end of my lecture for trigonometric substitution. I hope this has been useful, and good luck on your homework.